Hello everyone, myself Vikas T. Studying in SVCE Bangalore. Today I am going to discuss about the topic Lagrange's theorem in DMS, a fundamental theorem in group theory. Lagrange theorem is a fundamental concept in group theory, a branch abstract algebra. It establishes crucial relationship between the order of group and order of subgroups. Definition of Lagrange's theorem. Lagrange's theorem states that for any group, the order of subgroup divides the order of the group. The order of the group is the number of elements in the group, and the order of subgroup in the number of elements in the subgroup. Example, consider the group of integers modulo 6. Under addition, the group has 6 elements 0, 1, 2, 3, 4, 5. Subgroup 0, 2, 4 has 3 elements. Notice that 3 divides as 6 stated by Lagrange's theorem. Importance of Lagrange's theorem. Mathematics and beyond, it provides insights into structure of finite groups and allows us to understand the relationship between groups and subgroups. Number theory. Lagrange's theorem plays a role in a number theory, particularly in study of modular arithmetic and factorization of integers. Coding theory. Theorem applications in coding theory, where it used to construct error correcting codes by understanding the relationship between groups and subgroups. Cryptography. In cryptography, Lagrange's theorem is relevant to study infinite groups, which are essential for building secure encryption algorithms. Lagrange's theorem supplies finite groups, meaning groups with a finite number of elements. The theorem does not hold infinite groups. The group also have a well-defined operation as satisfies operation properties such as associativity, identity, inverse elements. Finite group. The group must have a finite number of elements, the crucial for the theorem application. Well-defined operation. The group must have well-defined operation that satisfy the properties of a group such as associativity, identity, and inverses. Proofs of Lagrange's theorem. The proof of Lagrange's theorem involves constructing a set of distinct cosets subgroup within a group. These causes phantom of the group, construct codes, partition of the group, order division. Application of Lagrange's theorem. Lagrange's theorem finds an application in various mathematical disciplines, well as in the fields like computer science and cryptography. It is a versatile tool for understanding structure and groups and their subgroups. Area. Number theory, analyzing modular arithmetic and factorization of integers. Coding theory, cryptography, and analyzing security cryptographic algorithms. Relationship to other theorems. Lagrange's theorem is closely to other fundamental theorems in groups such as theory, Cauchy theorem, Solo's theorems. Cauchy theorems. Cauchy theorem states that for any prime numbers that divides an order of group, there exists element of order P in the group. Swallow's theorem. Swallow's theorems provide more detailed information about the existence structure of subgroups of a group. Order is a power of prime number. Limitations of Lagrange's theorem. While Lagrange's theorem is a powerful tool, it has limitations. The theorem only provides an information about the order of subgroups. It does not guarantee for the existence of a subgroup every division of a group order. It also doesn't provide the information about the structure of subgroups. Existence. Lagrange's theorem does not guarantee existence of a subgroup divisor of the group's order. Structure. The theorem doesn't provide the information about the structured subgroups. Examples of Lagrange's theorem. Consider the group of symmetric squares. The group has 8 elements presenting a different ways to rotate. Reflect the square. The subgroups of order 2, 4, 8. Note that each these subgroups divides the order of entire group. Symmetries of a squares. The group of symmetries of a squares has 8 elements. Subgroups of order 2 and 4. Basic concepts: a group of sets equipped operation that satisfies certain conditions. The order of group is the number of elements in that group. Statement of Langevin theorem. Langevin theorem states order of subgroups divides an order of group. Implications of a theorem. One immediate implication: it is every subgroup's order of a factor of the group's order. That leads the conclusion that group of prime numbers simply have no trivial subgroups. The theorem helps in determining possible sizes of subgroups of a given group. Proof overview. The proof of a Langevin theorem involves partitioning group into costs. The left cosets of a subgroup are used to demonstrate theorem. Each coset has same number of elements in the subgroup. Cosets. A left coset is formed by the multiplying all elements by fixed element. Each element belongs to exactly one coset. Counting cosets. The number of distinct left cosets is given by the index. The index can be defined as GH. The total number of elements equals to the cosets multiplied by the order of H. Direct consequences. If G is a prime order, it can only have the trivial subgroup and itself. This means there is no trivial proper subgroup such groups. Application. Langevin theorem is crucial finite groups. It aids providing importance theorem in group theory such as Cauchy theorem. Langevin theorem in number theory. It has an application behind the group theory such as number theory. It helps in understanding the structure of the multiplicative group of integers modulo. Relation to Swallow theorem. The Swallow theorem extends the ideas of Langevin theorem. Limitations of Langevin theorem. Langevin theorem does not apply to infinite groups. The theorem gives no information about the subgroup structure in infinite groups. Additionally, it does not specify uniqueness subgroups for a given order. Examples of non-unique subgroups. The group which has order 6, there are multiple subgroups of order 2. These subgroups illustrate the multiple distinct subgroups can share same order. Langevin theorem does not indicate the number of each subgroups. Historical content. Langevin theorem was introduced Joseph Louis Langevin in 18th century. The theorem played a significant role in the development of group theory. Langevin's work led to groundwork of mathematical Galileo and Galilei. Related theorems are Cauchy theorem and Abelian theorem built on Langevin theorem. Each these theorem contributes to a deeper understanding of a group structure. The interconnections between these theorems highlight the richness of group theory. Advanced applications. Used in cryptography, especially algorithm relying group structure. It assists in the analysis of a cyclic groups. Application extend coordinating theory, combinational designs. Summary of key points. Provides a foundational group theory. Understanding subgroup order helps in evaluating structure of finite groups. Theorem has fair implication across various fields of mathematics. Conclusion. Langevin theorem pivotal result in abstract algebra. Its implication extend beyond the theory practical application in various disciplines. Continued study in a theorem enriches understanding mathematical structure. This presentation comprehensive overview of a Langevin theorem, its significance and its application across various fields. Conclusion and summary. Langevin theorem is a fundamental theorem in group theory, establishing a crucial relationship between the order of group and the order of subgroups. It has a significant implications in various fields of mathematics and beyond. Understanding Langevin theorem provides insights to the structure of groups and allows us to analyze the relationship between groups and their subgroups. Langevin theorem is a fundamental theorem in the group theory, establishing crucial relationship between the order of group and order of subgroups. Thank you.